So now let's go to the concept of atomic number, atomic mass, and isotopes. Okay? So a while ago, we talked about the subatomic particles. So if you can still recall, we have three subatomic particles, namely protons, neutrons, and electrons. Now, how are those three subatomic particles relevant to our topic right now, which is the atomic number and the concept of atomic mass? Okay? So if you have your periodic table of elements with you, you will see or you will find that each of the elements in the periodic table has these numbers. You have number 2 and you have number 4. Okay? So what does this two numbers mean? Well, this number on the top of the element symbol is what we call as the atomic number. And the atomic number is the number of protons in the nucleus of each atom of an element. Again, the atomic number is also the number of protons in the nucleus of each of the elements. So let's say, for example, we have helium here. Helium has 2 protons because the atomic number of helium is 2. In a neutral atom, the number of protons is equal to the number of electrons. So the atomic number also indicates the number of electrons present in the atom. Now, when we say that the atom is a neutral atom, meaning that there is no net charge or the charge is 0. Okay? When the charge of the atom is 0, then that means that the number of protons and the number of electrons is equal. The chemical identity of an atom can be determined solely by its atomic number. Okay? Please try to remember that. Next, we have the concept of mass number or the atomic mass. Now, the mass number or the atomic mass is the total number of protons and neutrons present in the nucleus of an atom of each element. So, where will you usually find it? You will usually find it at the bottom part of the element symbol. Okay? So, in this case, helium, its mass number is 4.0026. But for the purpose of computation, we have to round this one off to the nearest whole number. So it is safe to say that the mass number of helium is 4. Okay? With an exemption of hydrogen. Hydrogen has only 1 proton and no neutrons. Okay? Except for hydrogen, all atomic nuclei contains both protons and neutrons. Now, how to compute for the mass number? The mass number is given by the number of protons plus the number of neutrons, or atomic number plus the number of neutrons. And if you're going to look for the number of neutrons, you just need to subtract the atomic number from the mass number. Okay? So if we're going to go back to our example a while ago, which is helium, the mass number of helium is 4. So if we're going to get the number of neutrons of helium, we have to subtract 2, which is the atomic number of helium, from the mass number of helium, which is 4. So 4 minus 2, that is 2. Okay? Meaning, helium has 2 neutrons. Now, let's go to how to denote the atomic number and the mass number. So, there is a proper way of writing down the mass number and the atomic number of a certain element, especially when it comes to nuclear equations. Okay? So, the accepted way to denote the atomic number and the mass number of an atom of a certain element is as follows. So, you have the mass number, which is A here, which will become your superscript. X represents the element, and then the atomic number, Z, will be the subscript. Okay? Remember, guys, that the atomic number is also the number of protons. And then the mass number is the number of protons plus the number of neutrons. Now let's go to nuclear reactions. What are isotopes? How to balance nuclear reactions and the types of nuclear reactions. Okay? Now what are isotopes? Isotopes are atoms of the same atomic number but different mass numbers. Now in some instances, it will not always be the same. Okay? Again, if you can recall, the atomic number holds the identity of a certain element. Okay? So, isotopes are like varieties of a certain element. They are all the same, but one atom could be heavier than the other. Now, let's take a look at our example here. Hydrogen has three isotopes. Okay? So, the first one is your normal hydrogen, which is also known as protium. Okay? It has one proton and therefore the atomic mass is also 1. Now, we have another isotope of hydrogen, which is called deuterium. Okay? Deuterium has one proton because the atomic number is 1. However, the mass number is 2. So it has an additional 1 neutron. Okay? Therefore, it is heavier compared to protium. And then another isotope of hydrogen, which is tritium, has one proton because the atomic number again is 1, but it has 2 extra neutrons. Okay? So those are isotopes. Atoms that have the same atomic number but different mass numbers. Now, Miss, why do we need to know this? Because isotopes are the ones involved in the process of nuclear reactions. Okay? Some of these isotopes, because they have extra particles inside of them, they can be a little bit unstable. Okay? And these atoms, they only want to be stable. That's why they undergo nuclear reactions to become stable. Okay? Now, isotopes may also be written using the element symbol followed by the dash and the atomic mass. Alright? Now, let's go to how we balance nuclear reactions. So hello everyone, we're going to talk about balancing nuclear reactions. So let's start off with magnesium 25, which is an isotope of magnesium. Okay, so if you will notice, 25 is written as, 25 is your atomic mass, and then 12 is the atomic number. And then we're going to add an alpha particle to magnesium 25. So how are we going to balance out and how are we going to know the product for this one? Okay, so let's try to identify first what is our atomic mass and the atomic number. Okay, so if you will still remember how isotopes are being written in a nuclear reaction, your A is your atomic mass and then the Z is the atomic number. So there. And all you have to do is to add the atomic mass and the atomic numbers together. So you get 25 plus 4, that is A plus 1. Okay? So you have to identify what is letter A. A is equals to 28. Okay? Now let's go to the atomic number. The atomic number, that's 12 plus 2 equals to Z plus 1. So that is 13. And that's what you're going to write on the part of the product. So your A is 28 and Z is 13. And you just need to look for the element number 13 in the periodic table. So the answer is there, aluminum. Okay? So that's how you balance out nuclear reactions. Thank you. Now, let's go to the concept of radioactivity. Now, what is radioactivity? Radioactivity is the process that involves the emission of energetic particles of an atom, such as elements, a new element, electrons, protons, neutrons, among others. Now, if you will recall a while ago, during the balancing of nuclear reactions, again, certain isotopes undergo the process of nuclear reactions to become stable or to create new elements. Okay? Now, radioactivity is a part of it. Okay? This is the process in which an element or an atom becomes stable by releasing energetic particles. Okay? Since the energy inside an unstable isotope or an unstable atom is really high, okay, in some instances, they need to release those particles so that the atom can become stable. And that is radioactivity. Now, radioactivity or these energetic materials are a part of the EMS or the electromagnetic spectrum. So if you will notice in front of you, the electromagnetic spectrum is composed of different wavelengths, okay, ranging from radio waves up to the most dangerous, which are the gamma rays. Okay, and these parts of the electromagnetic spectrum are being emitted by different particles. Okay, especially you have your X-rays and your gamma rays, which are highly energized wavelengths that can cause damage to, let's say, for example, to us, to humans. Okay, uh, whenever an atom would undergo radioactivity, okay, or would release energy. Now, there are several types of nuclear reaction. The first one that we have is an alpha decay, just like just like our example in the balancing nuclear reactions. Okay, so alpha decay is the loss of an alpha particle. Now, if you will notice, whenever we say alpha decay, there is the emission of an alpha particle. Okay, meaning that the product is a new element plus an alpha particle. Again, an alpha particle is similar to a helium-4 nuclei, only that this one doesn't have any electrons. Okay? So this one happens when the nucleus emits an alpha particle. So alpha particles again have a positive charge and equivalent to the size of a helium nuclei. So the symbol is like this, or the alpha symbol. Okay? So what are the examples of an alpha decay? Let's say radium-226 undergoes an alpha decay, and that becomes radon-222 with the release of an alpha particle. Okay? We also have uranium-238. It becomes thorium-234 with the release of an alpha particle. Alright, so now let's go to beta decay. Now, beta decay happens when there is a loss of a beta particle. Now, what's a beta particle? A beta particle is a negatively charged particle that is much smaller than an alpha particle. They are equivalent to high-speed electrons. And this one happens when a neutron coming from the nucleus is converted into a beta particle and an electron, and a proton rather. Okay? So if you will notice here that even though you have the release of a beta particle, the atomic number increases. Again, it's because of a neutron being converted into a proton. That's why the atomic number increases. So, just like in this example, carbon-14 becomes nitrogen-14 with the release of a beta particle. Radon-228 becomes actinium-228 with the release of a beta particle. Okay? So, actually, either of these two are the symbols of a beta particle. Alright? But for our use, or for your understanding, you may use a beta particle or the beta symbol for beta decay. Okay? So now let's go to gamma radiation. Now, gamma radiation is basically the emission of gamma rays. Okay? So instead of releasing a particle, sometimes the nucleus may also release energy in the form of gamma rays. So if there is the release of a gamma ray, then there will be no particle release. So it will just make the atom more stable. Okay? So take a look at this example. Let's say we have uranium-238, which undergoes an alpha decay. Okay? It becomes thorium-234. Now, thorium-234, because it has still excess energy in the nucleus, may also undergo gamma radiation. And it becomes a more stable isotope or a more stable nucleus of uranium-234. Notice that there will be no change in the atomic mass and the atomic number. So your atomic mass and the atomic number stays the same if it undergoes gamma radiation. Again, it's energy that's being released, not a particle. Okay? Next, we have positron emission. Now, positron emission is the release of a positron. This happens when your proton in the nucleus is converted into a neutron. Now, neutron, as we all know, doesn't have any charge. But the charge can be released in the form of positron. Positron, positive electron. Okay? It has the size of an electron, however, the charge is positive. Okay, so what happens in the atomic number and the atomic mass? So the atomic number decreases by 1, as you can see here, because the proton or the proton also decreases. That's why your atomic number decreases also. And then the atomic mass stays the same. So for example, we have the positron emission of oxygen 15. Now, when oxygen 15 emits a positron, it becomes nitrogen 15. Okay? And then we also have electron capture. Now, in electron capture, this happens when usually the nearest electron in the nucleus is captured by the nucleus. Okay? So, what happens here? When an electron enters the nucleus, because of its high energy, okay, it combines with a proton to become a neutron. Okay? So, what happens when an electron combines with a proton? It becomes a neutron. So what happens in the atomic number and the atomic mass? The atomic number decreases by 1 because the proton is already combined with the electron, and then the atomic mass stays the same. Okay? Take a look at this example. Electron capture of mercury 201. So mercury 201 captures an electron. It becomes gold 201. Okay? Again, for you to verify whether the equation is balanced or not, remember what we discussed a while ago. Okay? So, the reactants or the parent elements or the atomic number and the atomic mass of the parent element should also be the same with that of the daughter or the product. Okay? And lastly, we have the bombardment of alpha particles. Now, in the bombardment of alpha particles, this is the opposite of alpha decay. This happens when an alpha particle enters the nucleus, okay, and gets absorbed, right? For example, we have the bombardment of beryllium with an alpha particle. Now, when beryllium-9 is bombarded with an alpha particle, take a look at this one. It becomes carbon-12 with the release of another particle, which is a neutron. Okay? Sometimes, this one may happen. Right? Especially with the case of carbon, because this carbon-12 is the most stable isotope of carbon. That's why it doesn't need this neutron anymore. That's why it's released. Okay? So if you will take a look at the atomic masses, 9 plus 4 is 13. Then 12 plus 1 is also 13. 4 plus 2 is 6. Then 6 plus 0 is also 6. So this one is a balanced nuclear reaction. Okay? So I hope that this lesson is clear for you. You may send me a message if you need to consult regarding this lesson or if you need to verify something about this lesson. Again, thank you for watching.